So fantastic. Thank you very much for taking the time out of your day to come to this session. My name's Chris Johnson. I'm a solutions architect from AWS in the UK. Joining me today is Michael Heimlich and Ronan Artsy from AstraZeneca, part of the research and development part of their scientific business. And really the topic today is about how AstraZeneca was able to process 7 times the amount of data, but was challenged with doing that in 1/10 of the time available to them, processing 20,000 exomes in 20 days. So we're going to have a look at design principles that support that type of business project and how you can look at leveraging some of those aspects to deliver on those projects. So what can we expect from today? We're going to have a look at something called the AWS Well-Architected Framework and how best practices can be learned from that when you're thinking about moving workloads and applications to cloud. We'll look at some of the design concepts that the AstraZeneca team used and that are referenced through that framework, using decoupled architectures to scale your applications effectively. And then we'll think about how we might be able to move some of those to event-driven architectures to change the way we're developing some of those applications. But then most importantly, we'll look at actually how those types of design principles are applied in practice and have a chance to listen to Ronan and Michael. So what is the Well-Architected program? It's the results of interactions between AWS and its customers, looking at best practices as you look to move workloads, applications, and environments to the cloud. It's built into a number of principal pillars that help you think about the best way to make use of that application when it does migrate. Similar to how when you log into the AWS console, you see the Trusted Advisor framework. So we're thinking about reliability, how to make the application performant, to make it secure, optimize for cost, and more recently, we've added a 5th pillar, which looks at operational excellence and how we can deploy applications in an effective way, and how can we manage them once they're there. So I want to take 5 minutes just to take an opportunity to have a look into each one of those pillars and think about, from a design perspective, what are the aspects that I need to think about? So reliability. We want to make the application available and reliable and fault tolerant. So we need to think about making use of multiple availability zones and ask ourselves whether or not multi-region is something we need to do for a latency perspective for the consumers of that application. We need to think about how the environment is going to scale. What triggers will define it? How is the auto-scaling group going to be defined, both to scale up, but just as importantly, how to reduce the scale of that application back down, and how fast should that scale up and scale down happen? How are we monitoring for availability and faults of components within that application architecture, and defining ways to remediate those faults when they occur, rather than just simply generating tickets or incidents that are assigned out to humans. Let's look at architectures and design principles that allow us to mitigate those faults from the point of them being detected. Hugely important to security, especially in the context of some of the workloads we'll talk about today. Thinking about how we're going to manage identity and extend or federate that identity in towards the application that you're hosting from AWS. How are we encrypting data in flight and at rest? So if we think about using AWS Key Management Service or Cloud HSM, there's a good principle to think about in terms of you're providing access to decrypt and encrypt data. But are those users of those keys separated from a principal perspective from the administrators of the system who are able to generate, revoke, and delete keys? Thinking about security event and incident management, thinking about being able to generate alerts that, again, aren't just simply generating incidents or tickets in a system, but are mitigating those as soon as they're detected. So take, for example, our CloudTrail service being turned off by either malicious or accidental errors. It would be great to have a service that responds to that immediately, that notifies me the service was disabled, but actually it's been turned back on, and this was the user or the application that executed that API call. When we think about AstraZeneca, beyond the program we're talking about today, but certainly in some of the well-architected engagements I've done with AstraZeneca, we've looked at healthcare and patient information data. So making use of dedicated instances so we can isolate the hypervisor layer to those particular workloads, enable them to be HIPAA compliant is a fantastic position for AstraZeneca. And that feeds nicely into how we think about compliance and governance of the platform as a whole, leveraging the compliance attestations that AWS has that help you then build on top of that with the way you manage and control access to your data and applications to have a great relationship with the auditors, the business consumers, and end users of that platform. The new pillar that we've added recently, operational excellence. As I say, it's not just about run and operate once that application is live. It's thinking about, actually, how am I deploying that application? Am I deploying it through a pipeline that I can repeat, I can orchestrate, and I can run multiple streams of those development environments in parallel with confidence that if I need to then release another update, it follows through that same process? How am I managing change in that environment once it is live? Am I making use of AWS config so that I can identify resources that make up my stack, my environment, and I can identify change to them at a component level, or even when things like auto-scaling adds more instances and removes them? Are we dealing with a change management tool that can accommodate the fact that instances aren't permanent? They're ephemeral. They'll be brought in when the application needs them, and then they're removed later on. But you're able to track its life cycle while it was part of that workload. And when you do, as architects, build out well-architected environments, architectures, environments that you want to advertise out to the business, are you leveraging service catalogs so you can publish those versions, those designs, out to the business and allow them to consume those designs? There's a win for you. You're able to see what versions of which application architectures have been consumed. The business can build on and consume those application environments quickly and easily, leveraging CloudFormation. But when you come to iterate on those designs and update them, you know which business consumers have used which versions, and you can offer them an easy path to being able to upgrade those particular stacks. Cost optimization is particularly important when we think about this particular workload. Huge amount of data to process in a short amount of time, and we want to be able to do it in a cost-effective way. So we're going to think about things like Spot, being able to leverage the Spot market to consume 7,500 cores to deliver the application workload that we're going to talk about today in a hugely cost-effective manner using the AWS Spot market. But it's just as important to think about the type of persistent stores you're using, the types of EBS volumes. Are you using GP2, general purpose SSD, or is provisioned IOPS the right mechanism for that? Thinking about these questions in how we build out these environments is part of the well-architected framework to help and guide some of these processes and questions that will come up. But cost management is not just about one particular workload. As your environment scales out, your business starts to use more services. The VPCs, the accounts will scale out with that demand. So being able to think about tagging strategies is one of the core first steps that I work with customers on, so that when instances and projects are deployed, you're able to put those accounts into a consolidated build structure. Using those tags, you can start to see where spend is coming from, what types of services are driving that spend. But more importantly, for the consumers, you can leverage budgets and forecasts to establish and alert them when predicted spend will reach a certain level. You're helping the business consumers understand where they are in terms of the budgets that have been set out, be those weekly, monthly, quarterly, or annually. Tagging is really crucial to being able to build out the models. But where we're going to focus around a little bit today now is thinking about performance. So about selecting the right AWS services. So am I spending my time extracting the maximum amount of performance out of the platform that I can for the time that we have available, that I need this processing and analytics job to complete? Am I making sure that I'm minimizing any lost CPU cycles or any I/O calls to the storage layer? Am I thinking about caching and storage architecture that effectively gives me the processing throughput that I need? Not just IOPS, but throughput as well to your storage layer. But ultimately, the outcome of these types of performance pillar decisions is a data-driven metric, a benchmark for your application that says, for this application version, I can achieve this amount of business level throughput for my application for this amount of cost. When you come to iterate on that design, when you come to look at leveraging new AWS services, you leverage that data-driven benchmark to compare whether or not you're achieving better throughput, better cost return. It helps the business understand why they take advantage of new services or the new design iterations that you've produced in that platform. So one of the questions we're going to think about now is SQS. One of the core principles of the architecture that we'll talk about from Ronan and Michael is decoupling of those architectures, and SQS is a fantastic platform to provide that. It's one of the first services offered by AWS, cornerstone for service-oriented architectures, and provides a way for decoupling layers. And we'll have a look at what we mean in terms of those concepts. But it's asynchronous processing as well. So if I'm moving data between an ERP system and a CRM, if I have a synchronous link between those, then my end user interactions with that platform have to wait for the message to be passed between those systems. In an asynchronous model, I can allow those systems to interact directly as they would normally, and then behind the scenes, the asynchronous messages are being passed between the platforms. It's the same model being used when you're moving analytics workloads through various stages. So let's consider an example. I've got a tablet device which is leveraging the AWS SDK. It's placing a video file through that SDK up onto an S3 bucket. At the same time, once it receives that 200 OK back from S3, then it's leveraging the SDK to be able to place a message on an SQS queue. Now, this is where the decoupling is happening. That tablet device is isolated from the EC2 worker tier that is monitoring that SQS queue. So as more tablets are added, it doesn't impact, and they don't need to be aware of the EC2 worker layer. That SQS layer is providing a decoupling, so I can now scale the tablet devices that I need, the types of objects they're placing, independently of the layer that needs to process the objects that are being placed by those tablets. As more tablets are added, more messages go on the queue, and I can now scale those EC2 instances as I need to be able to do it, and separate from the tablet devices themselves. So it's a pull-based mechanism. It's providing me the ability to pull messages off a queue, and if an individual instance fails, that message becomes visible back on the queue again, and I'm able to continue my analytics work. The polling happens periodically, and you can do both short and long polling to those SQS queues. And this is a widely used common pattern that you see across a broad set of industry use cases. So what does it give me as an application owner or as a consumer of the application? I'm decoupling my application. I'm presenting scalability at both layers, independent of one another. I'm leveraging asynchronous activities so that actually my end user interaction with the tablet devices completes in the shortest possible time, and then behind the scenes the processing happens without them needing to be aware of that. And it's highly available. I can deploy my worker tiers in multiple availability zones, and I can leverage an AWS managed service that is spanning those availability zones, but it's managed by AWS for me. So as an architect or a technical designer, what do I need to think about? I need to think about these AMIs that build up that EC2 worker layer. Do they contain the right libraries and binaries that I need to effect that analytics work? Are they appropriately patched and configured? And how do I maintain that AMI? I need to think about how I'm going to scale my auto-scale groups. What will define a trigger? By how much will I grow that environment each time that trigger executes? And when should I start to scale back down and how quickly? And then I need to think about that message validity period. Think about when that message, how long should it take me to process that object? And therefore, how long should I wait until I put that message back onto the queue? So how does that change if we move to an event-driven architecture? We're starting to make the application more directly connected now to the process that I want to execute, the logic. Ultimately, what differentiates your application, what's driving your logic. I want to provide a way for the application to be more in control of executing that. And I want to define it in a way that is a trigger that executes my logic and scales with me as I need. I can then remove the undifferentiated heavy lifting associated with managing EC2 fleets, operating systems, infrastructure. Simply define a trigger and the business logic that I want to run. So how does that change in the model that we looked at earlier? Well, now with an event-driven architecture, I still have exactly the same tablet device, the same AWS SDK. It's putting an object, as it did, onto that S3 bucket. But now I'm using an event trigger to say, when an object is placed in S3, I want you to execute this Lambda function. Lambda function is my business logic layer. I don't need to think about infrastructure. I don't need to think about operating systems. I just define the business logic that I want to execute. And because I can run Lambda functions with roles from identity and access management, I'm able to define the services that I want it to be able to interact with. So I've triggered a notification, which has executed a Lambda function, which is also invoked for me, Elastic Transcoder, to start transcoding that video file and placing the resultant file back into S3. If there are no puts, there are no Lambda executions. There's no business logic being executed. And if I scale the number of tablet devices exponentially, then Lambda will run with me as I need it to be able to do. So notifications aren't just necessarily about triggering one Lambda function. It also enables me to publish some subscribe models using SNS. So if I want one event to trigger multiple things, then I can do that. SNS provides me a mechanism to fan out that logic. I can also interface with SQS, so it's not about having to choose one or the other. If I've got longer second-stage processing that I still want to do in an asynchronous form, aggregations, summaries, separate reporting requirements, you can still notify out and place messages on SQS and have that second-stage processing happen. But of course, in the use case that we're talking about today, we're invoking Lambda directly. But it's not just about simple architectures with one stage of analytics. Certainly in the discussion that we'll talk with Ronan and Michael, they had multiple stages of analytics. And the same is possible here. That Lambda function that's been created and triggered by that S3 put can still continue to talk to SNS to do a second stage process that feeds into a message that I receive on SMS or an SQS message, email, HTTP, HTTPS endpoints, or again, second stage Lambdas. I've moved from a pull-based architecture to a push-based architecture that enables my application to be the controller of when this happens. So the advantages, I've reduced operational complexity. I've removed the need for me to worry about EC2 fleets, the worker layer. I've just defined business logic that matters to me. It's made it more cost-effective, and I'm going to talk about that towards the end of the slide, actually, when I compare decoupled to event-driven architectures and how that impacts the commercial proposal. So are there aspects I still need to think? Well, I think absolutely there are still aspects. As an architect or a technical designer, what do I need to think about? Virtual wiring. You may have multiple layers of Lambda functions that are going to do processing for you. You may have SQS driving longer poll activities that need to happen. How do I plug them together? Well, up until this morning, it would have been wiring them together with SNS. And then thinking about how you manage dependencies and parallelisms of those particular components. With step functions, we provide a service that really simplifies that greatly now. You can manage that visual workflow of how you want these functions to roll from parent to child and through the workflow that you want to execute. But there is a mechanism here that still needs to be thought about, which is how many transformations do you want to do within one Lambda function? My recommendation is try and simplify the functions down so there's almost like one input and one output from your Lambda functions. Because when you're trying to triage or diagnose business logic, and why you're not ending up with a result that you were expecting, or there's a change in the output that you were expecting, it's a lot simpler to work on the basis of each Lambda function having one input and one output, because it reduces the scope of change, reduces the scope of code that has to be reviewed, and you can still wire them together, so it's simpler then to deploy the mitigation. Think about storage space. Each Lambda function comes with 500 meg. Is that appropriate? And as we talked about in the well-architected framework, it encourages us to think about what types of persistent stores do I need access to. And think about embracing the ability just to focus on the logic layer. Think about what differentiates your applications, your development teams, to help them push forwards and not become bogged down with thinking about kernel or operating system dependencies that hold you back from some of these architecture principles. So when we think about it, I said I'd mention about the commercial model, so let's compare the two. And it's not about having to choose one or the other, it's about combining the two, but understanding there is quite a significant difference when you look at one. If I consider a decoupled architecture, I'm paying by the hour for EC2 instances at that worker layer. But if I move to an event-driven architecture with Lambda, I'm paying only when I'm executing Lambda functions, and I'm paying by the 100 milliseconds. From a scaling perspective, in an EC2 world, I can either scale horizontally or vertically, but I've got to manage those CPU cycles and making sure they're effectively used, and I'm scaling up and in alongside my requirements for my application. In a Lambda world, they're stateless executions of functions. AWS takes care of the invocations of that code for you, and we will scale as you continue to drive more and more invocations to us. And if there are no invocations, there's no cost. In a storage world under a decoupled architecture, of course, you have EBS volumes, hard drives attached to your EC2 instances that run the operating system. In an event-driven architecture, there isn't any visibility of that. You don't see that layer at all. You just focus on the storage layer that's needed for your logic to process your data. And it allows you to think about things like DynamoDB and S3 as different storage layers just for your application logic. You see how it sort of focuses you towards one direction. But ultimately, there's no difference from a network perspective. So this is why it simplifies the design. You can leverage both within one environment. So with those principles in mind, I think it's important to understand how some of those design ideas were put into practice. So I'd like to ask Michael Heimlich to come over and talk to you about how the project was able to process.
Thank you, Chris, for that excellent introduction. So Ronan and I are going to take you through our journey of how we used many of the principles, the architectural principles that Chris discussed in his lead-in, how we were able to process many more samples than we had processed previously in a highly restricted time frame. And we hope you enjoy the journey with us. Let me give you a brief introduction to our company, AstraZeneca. We're a global biopharmaceutical company. Every day, the focus is on the science and on the patients. Now, Ronan and I work in a section of the company called Research and Development Information. We are part of IT. However, we are the science-facing part. That means we interact on a regular basis with the scientists. Many of us have advanced science degrees, so we know what it's like to be on the other side. This really helps us in understanding the problems that the scientists are facing. And our group has been tasked with operating in mode of similar to a startup that gives us great agility and the ability to tackle the problems in a really timely manner. So AstraZeneca has announced a genomic strategy with the idea that embedding genomics into the research and development will lead to many advantages. For example, being able to deliver novel insights into the biology of diseases, enabling the identification of new targets for medications, being able to select patients for clinical trials, and allowing patients to be matched up with the medications that are going to be best suited for their treatment. And we're going to leverage up to 2 million human genomes, roughly 500,000 coming from our clinical trials, and the balance coming from our partners that you can see up on the screen. Now, a little bit of genomic sequencing 101, not to get too deep, but basically to give you an idea of how we transform the human genome into a digital representation. So if we look on the left side, what we do is we start off with the DNA, chop it up, add some chemistry to it so that it can be detected by the sequencers. In the middle now, you can see that we have put the samples in the sequencer so that the nucleic acid bases can be read in their correct sequence. And then at the bottom of the middle section, you can see that we get a file output. These files for a particular sequencer can range up to about 1.5 terabytes in size. This represents our big data problem. And it's not just that it may come from our sequencers, but can come from our partner sequencers as well. And then on the right side of the slide, you can see the part where we do the processing and the alignment. We're aligning these various bits and pieces of genome to a reference that has been determined by multiple sciences to be as accurately as possible the basic genome of every human being. This part of the problem constitutes our compute problem, where we need to throw massive compute resources at it. Now, I've been talking about genomes. The project is about exomes. What's the difference? Why do one versus the other? So with exomes, you're dealing with a very small part of the genome. The advantage, though, is that you're working with a part of the genome that represents about 85% of the disease-causing areas, so you get a real good bang for your buck. Because the overall size is small, it reduces your cost for storage and processing. What it also means is that you can process many more samples. Advantages of using the genome is being able to identify disease areas that are not in the exome, but also if you're going to work with species that are not human, because there aren't really good exome models available for monkey, dog, etc. Going forward, as compute power, storage costs all shrink, it will be more and more advantageous just to go with a whole genome and not necessarily worry about using exome. Now, what is it we're trying to look for when we're doing the sequencing? So we're matching up the two, and for oncology, we're matching up the tumor's genomic sequence with the reference, and we're trying to find mutations, things that are messed up. These are what lead to diseases, and so I'm just showing you here some examples, not all examples, of types of mutations where chunks of DNA can be removed, where they can be replicated, where they can be transferred from one gene to another gene, many other types. The point here, though, is we need a tool called a variant caller, which is going to be able to scan for all of these mutations and identify them correctly.
Thank you, Michael. So as the name of the project is called 20K in 20 days, just a little bit of reflection about 20 days, right? So, when the project was thrown at us, we were in the midst of defining our future scientific computing platform, right? So we had to, on one hand, kind of look into the future, however, really, really responding to our clients immediately. So basically, the 20 days happened while kind of building the airplane while we were flying, right? So if you would ask me the same, how much would it take you now that you don't have to build it? So it probably will take 4 days at the same amount of data that was thrown at us. So that's one aspect that we need to remember. The other one is a kind of a humbling reflection, which is, yes, we did it in 20 days. But that is really, really based on a lot of hard work that has to be done up front, right? To convince a business that was not used to think like in a cloud mindset, right? Was not necessarily ready for that. So all of that evangelizing work and so on definitely has to be thought of, right? So the journey towards the 20 days started much earlier. It started by our conversation with our customers, right? Convincing them that this is a new era of IT, new era of IT technicians, right? We do think unlimitless when it comes to infrastructure, right? Try to dream. Come to us with dreams, and we'll collaborate with you and act on it. We also needed to work with our colleagues on IT, on legal, and compliance, right? To talk to them and make sure that they feel right about we're doing the right things, right? These are a little bit different concepts. We have to talk about them. We need to understand what's the difference. We need to understand what is done different and better in the cloud. And they agreed, and they do understand it now, right? And having their approval and support is critical moving forward. And the last one is actually doing things right? Working with project management, working with selection of technology, selecting the right tools for the task at hand. So one of the elements that is crucial in that kind of discussion with the business is developing what we call the stack security and compliance model. I mean, a lot of you will identify that one as a derivative from the Amazon or the cloud kind of shared responsibility model. It was critical for the business to understand that there are layers in a solution, right? There is the cloud itself, right, that comprise of both the infrastructure and the enabling tools. There is another layer that we call it the R&D or the easy R&D cloud. That's the platform that we, as a group, had developed to be a container for innovative solution. And then on top of all of that, there is the place where the application itself, right, the specific business problem will be deployed. So understanding the layers is extremely important, but also giving them the confidence that when you go on a solution that goes across the layers, right, we can identify who's responsible to what layer, right, and give them confidence that all the controls, the right regulatory and security are being in place. So if we dive a little bit into, again, genomic is a sensitive personal data. I mean, I'm sure you can understand that your genome is basically your fingerprint, right? It's highly identify you. One of the challenges around it, by the way, it's not only disclosing potential information about you, it will potentially disclose information about your parent, right, about your sibling. And there are many questions about what is personal data in a genomic space, in a genomic phase, right? What are the legal implications? What are the ethical implications, right? When you give a consent to work on Genome, what does that mean? So Genome had challenged both AstraZeneca as well as the industry, right? We took no risk in that point, right? We went to the highly secured, assuming constraints on us on the highly sensitive data from our perspective. So we talked about our model, and especially given the fact that the information is so sensitive, it was crucial to make sure that we apply it into the model, right? Having the business go through it. So in a sense, the layers that you see before, you've seen it, you had the cloud layers, we have the AZ cloud platform, right? And we apply that into the Genomic project itself. On the right-hand side, you can see some of the constraints that we had to deal with. Some of them are industry regulatory constraints, like the HIPAA, right? This is about protecting against risk in releasing personal information. So that's one type of constraint. The other one is basically, where do you get the data from? We had a source of data, endpoint, right, that they had their own kind of regulatory requirements. That's called dbGaP. In that specific case, this is about protecting from exposing through genomic data. And on top of it, there is obviously the AZ rules and restriction, right? We do have on top of it quality requirements, regulatory requirements, and so on. So applying that, again, talking to the business, it should be really, really clear. What does AWS is responsible for? What does our team as a platform building is responsible for? And then what is the project team responsible for? Michael?
So as we know, technology, science are always improving on a practically daily basis. And I mentioned earlier about reference genome. So improvements in the reference genome as scientists are able to better quantify and identify the parts of the human genome, those are constantly being updated. In terms of our variant caller, AstraZeneca has developed a tool called VarDict. It's roughly 20% better able to identify these mutations that I've been talking about, and it's something that we have contributed to the open source community so that everybody has access to it. And of course, with cloud, we've got new, much improved computational capacity available to us. So for all of these reasons, we had a project. We had access to the Cancer Genome Atlas with these thousands of exomes sitting there, but they had been aligned to the earlier version of the reference genome, HG19. Now we were going to want to align them to HG38. The tools that had been used to do the variant calling on those exomes were not done with VarDict. So we, with our VarDict, with the ability to identify an additional 20% of those mutations, felt that this was a challenge that we wanted to undertake. And then we had our time constraint between Thanksgiving and Christmas, which made things very interesting. From a data standpoint, I mentioned earlier about big data. These 20,000 exomes took a little over 270 terabytes of raw genomic data. Now, if we wanted to process those on premises, yeah, good luck. We did not have the storage capacity to even think of bringing them down. If we had the storage capacity to bring them down, it would have meant taking our computational capacity and telling everyone else, sorry, you can't do anything for a year because we're processing these exomes. Then there was the idea of transferring these down via internet, and with our connection, 1 gigabit's not too bad, gigabit per second, but with 270 terabytes of data, now we're looking at 25 days. Again, something you really don't want to have to undertake. And even practically more critically was the experience that we had to date, which was under 3,000 exomes in roughly 3 years. Now we're being asked to process 7 times more of these samples in less than a month. So you can clearly see we were faced with challenges.
So as you see, we have to think different, right? We just couldn't continue doing what we did before in order to meet the challenge. We were constrained by hardware. We were constrained by process. If you look into the old way of doing, AstraZeneca was doing exome analysis or whole genome analysis, right? The difference was that we did it on small quantities. So the scientist will download all the information. Once all the samples are down, he will submit jobs into a constrained environment, our HPC. Once this is done, he will run some post-processing, and we will have his results. So this is awesome, right, when you talk about small quantities. When you talk about 20,000 samples that has to be brought in, right, and then you need to apply computation, analysis computation, and then post-processing, you need to work different, right? So when we looked into the cloud before, we tried to mimic the way we were working, right? We will launch a cluster in the cloud. The scientists will upload data, run it through the cluster, get results. But for this specific project, it just couldn't work, right? So first of all, given the number of people we had, and in general, you need to think simple, or try to simplify the problem, right? And we had three major pillars over there. One, we had an ingestion problem. The other one, you had an analysis problem, and then you have to take the right data back home, right? And you need to somehow allow to orchestrate across those pillars, right? If you look a little bit behind the scene of the ingestions, right? So we had applied some of the well-architected thinking when you think about distributed environment or highly parallel environment. It has to be decoupled. We have to decouple between those who were asking for the job to be done and those that will execute each one of the portions, right? It has to be a scalable architecture. It has to relate to the demand, right? We need to be able to grow the system and shrink the system based on what is being requested from us. It obviously has to be asynchronous, right? Some of those jobs are running in the background, and when they'll be done, we'll have to move to the next phase. We really think that some of those portions were a shared environment, right? We're trying to parallelize everything, but some of those components you'll see later are shared environment. We need to apply high availability to make sure that there is no friction around failing component within those elements. And we need to take out any waste in the process. So event-driven, data-driven is extremely important, right? I do not want to wait. Once a certain portion of my computation is ready, I need to funnel it to the next phase. So we had used some of the construct that Amazon is providing us in order to demonstrate this environment, right? We're definitely using EC2 instances. What's nice about those instances, when you analyze the type of data to be brought in, you find that there are different sizes of files, right? You might want different type of workers to work on those files when you bring them. You might to wire different type of EBSs to those instances. So we had definitely used those concept of configuration groups. We had used scaling groups when we wanted to grow and shrink that environment. In that specific problem, it was highly convenient spot instance or the market, right? In order to shrink the cost of the ingestion process. We definitely used the huge superb bandwidth that Amazon had provided us. And that bandwidth goes two ways, right? One is towards the source endpoint, and the other one towards the storage itself. We couldn't do that at home. And the last piece is S3. S3 was really, really good for us, right, as a data plane to be able to exchange information between the ingestions into the analysis into the post-processing. And I'm not sure that I mentioned, but I mean, following Chris' kind of design, SQS had helped us tremendously as a medium to exchange work between workers, between clients, and executors. These graphs are telling a little bit the story, right? And you can see that we started very, very cautiously. You know, when we looked into the problem, people might think that the analysis was the kind of the element that worried us. But in a sense, ingestion worried us a lot, right? It was really, really depend. I mean, can the source endpoint really meet the load that we needed, right? I mean, we used it in a very small scale when we worked at home. We use GeneTorrent as a way to access and get some files from the TCGA. But in a sense, that was the biggest problem that I was we were worried about, because if we cannot get the data, that's an issue. So we started really, really slow, right, developing those ingestions. And you can see on the left side, we got about 52 terabytes per 6 days. Okay, that gave us a little bit confidence. Yes, we can do the project, right? And then we left off, and we started to build the analysis orchestration. We came back on the right-hand side. You see that we got a little bit even more confidence, so we turned the dial a little bit, right? And you can see that we brought about 63 terabytes in 1.5 days. Awesome, this is good. And then we went to continue work on the analysis, right? Because there was a lot of analysis to be done. So this is the flat line. At the end of the day, when we really, really wanted to have the whole factory working, we just turned the dial, right? And you can see that we bought about 85 terabytes in 2 days. So all in all, if you just aggregate those, you can see that 270 terabytes were brought about in 4 days, right? And then that was really pleasing us. Looking into the, a little bit behind the scene of the analysis portion, you see we use the same construct, right? It was the same architecture. The only difference you might find is that the little piece in the middle called alignment, right? And that piece was those pipeline engines that we used, right? That was a shared environment. What's nice about that shared environment, we could spin many of them. Those were clusters. But our workers had interface with those environments via an API. So that's the only difference into that environment. However, using API, using that kind of decoupling, helped us later on to replace those components as needed. Again, SQS was used as the medium to exchange information between a requester to an executor. S3 did an excellent job, right, on consuming the data from the analysis. And we used Lambda, which I'll mention here, but we also use that on the ingestion. Immediately once we got the results in S3, we triggered the next step, right? So there was no waste on time between moving from one step to another. In this specific case, you can also see some slicer, but workers will touch on them later on. Again, a little bit behind the scene on this one. What's interesting about this one of our design principles was to reuse all the resources that we had. We had spawned some in the cloud. We did have an HPC internally, right? And we also had some appliance internally. So we wanted to make sure that we use the right environment for the right job. Some of the samples were brought in, at least at the beginning, just to make sure that the pipeline is running correctly. And what's nice about this architecture, using the SQS environment, using the concept of executors and so on, it doesn't really matter where the executor lives, right? Some of our executors live internally, on premises, some lived in the cloud, okay? It was just about the executor need to discover the environment, given the request itself, understand where does the data live, where is the pipeline that I'll use, and then utilize that the best. So this is a little bit different paradigm because most people believe that you're either all in the cloud or on-premise, and now we're talking about the project that within the project itself, we use system all over the place. This is another element over here, which is the slicer. So I mentioned the slicer. When we analyze the pipeline or the information flow, we realize that as you're doing alignment and then you're doing variance score, there is an opportunity to take the aligned file, right, and slice and dice it. Why do we slice and dice it? Because at the end of the day, we want to bring only those elements that we care for, okay? And Michael will touch on that later on. The slicer was a very simple worker, right? All he knows is that given a request to slice, he will go fetch the file, slice it, shrink it, put it in S3, right? And indicate, I'm done. Somebody else needs to take care of it. What's interesting about the slicer, again, we use the spot market heavily, and we just reduce the cost over there. We talk about workers that cost about 2 cents, right, or very, very marginal cost over there. We were very happy with using the spot to reduce cost for this kind of task. The other piece that is interesting about this one, we developed that one last. Okay, so you can just imagine, right, that the queue for slicing was just growing and growing and growing. So we counted with the fact that there is no problem to grow a queuing like that coming from Amazon, right? It's an awesome service on one hand. And then as we looked into the slicer, the slicer were aggregated into an auto-scaling group. The rules to shrink and grow were based on the size of the queue, right? So when you turn it loose, we just finished the queue slicing. I believe we got into 6,000 slides, right? If I'm not mistaken, within an hour or so, okay? So it's just amazing, just using that auto-scaling. We turned about, I believe it was 700 workers, just did the job and shrink to 0. So that's what really got us through the system. And the last piece was really, really easy, right? So we wrote actually an executor, this time live on premise, right? The executor looked into the I'm done kind of queue, brought the system, brought the files in, only the files that we needed, right? And also cleaned the environment after it. So there's no any residuals of any files that we don't really need. So all we brought is only what we need, and you can see how fast we kind of drained the queue, drained the environment, and got the message home.
So what did we build? We built ourselves a time machine. Now, it's not the kind of time machine where you get in and you travel to the future, but it's the kind of time machine where you bring the future closer to you, closer to the present. Now, you can see on the slide, we've got in green, we've got the bars to show how long it would have taken on our on-premises system if we had the storage, if we would have told everyone to stop what you're doing for a year while we take care of this project. And you can see towards the very left that, in fact, it took us less time to do in the cloud to transfer the data, analyze, post-process, slice, and bring it back down the limited amount of data that we needed, less time to do all that than it would have taken just to download the data to our on-premises system. So in this way, first off, we're able to get this knowledge to our scientists much, much faster. In this case, we shaved a theoretical year off of the time required, getting that knowledge to the scientists, and then being able to develop the medications from that and getting that to the patients that much sooner. This is absolutely critical. Also critical, again, this is a theoretical year, so that we couldn't have done this. So whatever knowledge we derive from this project would not have been available to us because it would have just been data sitting in a file store or sitting in a database that would have not been usable to us. So by having the availability of the cloud, it allowed us to turn that information into real usable knowledge. And not only we're shrinking time, we're shrinking resources. So as you all know, when you're dealing with an on-premise physical infrastructure, if you needed to scale it to do sort of thing that we wanted to do, it's a lot of capital expenditure, needs to go through a lot of approvals, and then when you're done, it's just sitting around consuming energy, electricity, and wasting resources. By doing it in the cloud, you're able to spool up all the resources that you need when you need it, take care of the problem, flip the switch, and all you're left with is a small storage footprint. And you're using operational dollars as opposed to capital expenditure dollars. So, how did we do? Processed just under the 20,000 exomes. We started off with our roughly 270 terabytes worth of raw data. We mentioned the slicing process. You can see that we took the 270 terabytes. From that, just 9 terabytes of the critical information that the scientists needed was downloaded. Very efficient process. We're showing just under 8,000 CPU cores that we needed to spin up. That was based on the time available to us. We could have grown that, shrunk that, depending on the time that we needed. In the end, in terms of the measurable outcome to the business, for CPU processing, storage, network transfer, we were looking at roughly $4 per exome that we processed, including all of the R&D ramp-up work that we did in order to get the system architected and running. So we were able to demonstrate that we could take a large number of samples, scale up the architecture, do the processing extremely economically, flip the switch, done. Then, as it turns out, a few months later, another project comes along. This time, we're dealing with whole genomes, larger data sample, larger files. At the same time, because of the agile nature of the architecture, we're able to swap out that middle portion. If you remember those 3 bars, the middle portion was the analysis. We were able to swap out our workflow orchestrator, whereas before, we were not able to use spot instances. This time, we were able to for our whole genome processing. We did only variant calling. We did not need to do the alignment part of it. It took 5 hours to do the work, and this was on every genome in parallel, because we could spool up as many instances as we needed to take care of the samples that we had. And cost-wise, $7 per whole genome for doing that variant calling. Again, flip the switch, systems down, negligible footprint. So what did we learn? Number 1, plan ahead. When I say plan ahead, in this case, it's absolutely critical getting your security and privacy teams on board as soon as possible. Particularly from a project management standpoint, it's key to make sure that these individuals are fully versed in what cloud technology is, how it works, how it's going to benefit the company, and how it's something to be embraced, not something to be feared. Right? It's also critical to understand your process. In this case, our pipeline, where we had been used to doing a piece of work the same way repetitively for many months, years. Now you're in the cloud. Now you have different tools available to you. You've got a platform that has managed services. You need to think about how best to take advantage of these services. And so you need to now get into that mindset of decoupling your architecture, making sure that some pieces, some things can be done at the same time that others are done. Very, very different mindset, but it's really key that you focus on that. Now, finally, you've got a business outcome. We were able to demonstrate because we could see exactly how much it costs to store the data, how much it costs to process the data, how much it costs to transfer the data. So at every step of the way, we have reports, we have numbers that we can give back to the business and tell them, you want to do this kind of processing, this is how long it's going to take, this is how much it's going to cost. At that point, I want to thank our great team at AstraZeneca for all the hard work. And thank you guys for coming and listening to us. And thanks to Chris and the AWS folks for all the hard work that they've done. It's a pleasure working with them. And please, folks, remember to do your evaluations. I think we have a few minutes for questions.